Okay, so today we're going to go ahead and go over the VSEPR theory, which is this just stands for valence shell electron pair repulsion theory. So if we remember, for example, let's look at the compound CO2. When we have bonds, for example, we have two double bonds here. These bonds are negatively charged regions. Okay, and negatively charged regions want to repel each other, so they're going to be as far away as possible as they can. So because these regions want to repel, all atoms, or rather all molecules, are going to form distinct molecular shapes, which we call VSEPR shapes, or molecular geometry. Okay, so let's go ahead and explore this. So when we're trying to figure out the type of shape an atom forms, we always look at the center atom. Okay, so we want to count the number of bonding regions around a center atom and the number of lone pairs. So, for example, if I look at this here, I have two double bonds on each side, but I only have what I call two bonding regions. Okay, so this would be, or you can think about it as electron regions. So this is one electron region, this would be two. So I have two electron regions, and I have no lone pairs around the center atom. This example, I don't have a center atom, so there's going to be a specific type of shape this forms, which we'll go over in a bit, but just keep in mind there's no center atom. Okay? In this center atom, we have 1, 2, 3 bonding regions, 3 bond regions, and we have 1 lone pair region, because this is a lone pair, right? Remember, lone pairs, those are pairs of electrons that are unshared. So we have 1 lone pair. Okay, if we look at this example here, we have around the center atom, we have 1, 2, 3, 4 bond regions, and we have 0 lone pairs around that. 0 lone pairs around that center atom. So we're always looking at the center atom to figure out what type of shape it's going to form. Okay, so let's go through a list here that I had you guys either copy or print, and we're going to go through some examples. Okay, so when we have, so let's say I have 2 bonds around an atom, such as the one we looked at, CO2. This also can be 2 or 1. I'll show you guys why in a bit. But let's say I have CO2, which has oxygen, double bond, carbon, double bond, oxygen. All right, so that's what it looks like. Whenever my center atom has 2 bonding regions around it and no lone pairs, that forms a straight compound with a bond angle of 180. So this would be 180. Okay, we call that compound, the geometry is called linear. So this would be linear. Okay, so let's go ahead and kind of move down the list here. So then my next compound, if I have something like, also actually going back to this, whenever we have 2 compounds, for example, such as HBr or like O2, whenever it's just 2, it's always going to be linear, because that's the only shape it can form, right? If I have H2 and if I draw that compound that looks like that, it's always going to be straight. So whenever I have 2 compounds, it's always linear. Keep that in mind. All right, let's say I have 2 bonding regions and 2 lone pairs. So this is an example of that. An example of that would be water, H2O. So H2O looks like this. H bonded to an O, bonded to an H. The oxygen has 2 lone pairs. So when we have 2 bonding regions, that's 1 bonding region, that's another, and 2 lone pairs, those are 2 lone pair regions, we have what we call, if rather than being straight, so rather than that compound being straight like this, those lone pairs on top push the electrons down, and it ends up being like this in what we call a bent structure. Okay, so this would be called bent, and it has a bond angle of 104.5. Okay, so this bond angle here would be 104.5. And again, we call that bend. All right, moving on here. So we're going to go through a couple of examples. This example actually doesn't follow the octet rule. So let's say this example, an example for this one would be 3 bonding regions, 0 lone pairs. So the example would be VF3. So we have boron bonded to 3 fluorines with no lone pairs in the middle. Okay, if you notice, this actually doesn't follow the octet rule, right? Because that's not. But there are compounds that are exceptions. This one would be an exception here. So I'm just draw the full structure here. It would look something like that. Okay, and we would end up with something that looks like this, with bond angle of 120. So bond angle of 120. So in 3D shape, this is still on the one single plane. It would look like this, right? So it would look, the molecular shape would look something like that, okay? And we call that, since we have 3 bonds, we call that trigonal to represent the 3 regions. Trigonal, okay? And because it's in a single plane, we call it trigonal planar. All right, I'll take a similar example, but slightly different here. So what if we have 3 bonding regions, same as this, but 1 lone pair? So an example of that would be NH3. If we draw the Lewis structures, you have to draw the Lewis structures to figure out the type of shape. You can't just really look at it and guess. You have to draw that Lewis structure first. Okay. So here we have 1, 2, 3 bonding regions, but we also have 1 lone pair. So when this is the case, we end up with a shape like this. Okay. So in other words, we have some lone pairs here. This would push everything down, and we end up with an angle of 107. And basically what's happening here is we have that same shape that's like this, but because we have electrons on the top of this, it pushes everything down, and it ends up being something more like, so I can make this here, like this, in which we would have, these would go down, and you would have kind of like a little pyramid, right? So these would form, it's kind of hard to visualize here, but I'll show you guys in the simulation. It would be like a little pyramid. That's why we call this here trigonal, still representing 3 bonding regions, trigonal, but now we call it pyramidal. There's like a little bonding, there's like a little pyramid in the bottom. Okay, moving on here, when we have 4 bonding regions with 0 lone pairs, such as CH4, like, for example, H, 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 H. When we have something like this, the bond angle is 109.5. So if you notice this bond angle, this is very similar to this, but the bond angle is smaller because those electrons on top really push everything down. Okay, this is going to be called tetra. Tetra for 4, tetrahedral. Tetrahedral is my shape. Okay. Then last of all, there's also a few more shapes that we're not going to go over. I'm just kind of going over the main ones with you guys for this course. This example here actually also doesn't follow the octet rule. So this one doesn't follow it, and this one doesn't follow it. In this example, we have 6 bond regions and 0 lone pairs. An example of that would be CF6, okay, in which we have sulfur, so like a sulfur molecule here, surrounded by 1, 2, 3, 4, 5, 6 fluorines, okay? And this example, whenever you have 6 bond regions, this makes an angle, the smallest angle that can be made is 90 degrees. 90 degree, okay? And we call that shape octahedral. So that shape is octahedral. Okay? The reason we call it that is because if you were to kind of map out the 3D shape of this, the 3D shape would have 8 sides, which that's why it's octahedral. Okay, you don't really know that, but can just give you guys some background information. Okay, so this is the final notes. That would be kind of everything you need to know. Okay, so you're going to be using this chart to basically look at compounds and name their shape. And in some examples, you have to draw them. So let's look at some examples here. So let's go back to where we were at. So when we have two bonding regions, such as CO2, we actually did that example right? That would be linear. As I mentioned here in this first example, whenever we have two compounds, it doesn't matter what they are, the only shape they can be is linear because they can only be straight. So this compound would also be linear. Okay. What about this compound here? We have in the center atom we have 1, 2, 3 bonding regions, but 1 lone pair. So let's look at my chart. 3 bonding. Well, that's 3 bonding, but that has 0 lone pairs. 3 bonding, 1 lone pair. What do we call that? Trigonal pyramidal. So this compound, the 3D shape would be trigonal pyramidal. Okay. So if I were to ask you to draw this compound, you would draw something like this, right? Like you would maybe draw this a different color. You would go. That would be the 3D shape. Okay. All right. What about this one here? We have 4 bonding regions, 0 lone pairs. Well, let's look at our chart. 4 bonding regions. Just go down. 4 bonding regions, 0 lone pairs. That matches. Well, we call that tetrahedral. So this compound here would be tetrahedral. Okay. If I were to ask you to draw that, well, let's say I represent green with carbon, right? So carbon would be green, and then I represent my hydrogens with a red. It would be red. And then I represent my fluorines with this is just, you could do any color really, but I'm just showing you guys. Let's say I represent my fluorines with a blue here. So it'd be here going back away from the paper, and another one coming towards you. Okay, that would be a 3D shape. So you will have an example where they're asking you to draw them. So make sure you know how to kind of visualize in your head what that 3D image would actually look like.